Greetings, gentle readers. July 8, 2026. Calm, sunny, not cloudless, about 80 degrees. Visibility unlimited. Today is in reading foundations from a study with Ross Finlayson and myself, a student and researcher and reader in foundations. Is the next box of books from my little library, some thousands of volumes that I've collected with generally a course to try to gather monumental or unique or soul source or those works that herald the developments and the tellings and the lenses of reading in foundations. The previous episode was a box of fiction, so usually these works are non-fiction, and so being non-fiction, then the accounts are as what's real and true. And so the accounts of fiction are in a sense true. They're true accounts of fictional tellings. And so that said, one comment from the previous video was that, well, maybe the next box of books would be all the documentation there is of the interface of Windows programming, or Win32 it's called, or Mac OS X is after Darwin, and display PostScript, and the accounts of the conventions and the interfaces and the graphical desktop operating system of the usual sort of a commodity sort. That then, though, the books I found instead are a bunch of philosophy and epistemology, meaning readings and semiotics and semantics and syntax and these sorts of accounts, and mathematics and so on. So that said, then I guess I'll just try to kind of read through these at a clip, and so there won't be too much particular detail explored in each of these works, yet to just kind of relate their setting in the great atlas, as it is, of mathematical independence. So the great atlas of mathematical independence is a concept here about the replete nature of the continuum and after competing rulialities of induction, of well-foundedness, well-ordering, and well-dispersion in usual accounts of axiomatic set theories, descriptive set theories, milieu of modern mathematics, that the great atlas of independence mathematical is to reflect on what are called the great giant monsters of mathematical independence, meaning contradictions, meaning, for example, paradoxes, and how paradoxes are to be resolved. So starting with Zeno's classical expositions of the superclassical, this is the usual work that's given as expressing the idea that in the contemplation of the accounts of motion in time and continuous time, then that various accounts of reasoning of the inductive sort that so follows, that just kind of carries along a line, would reach these inductive impasses, the unpassable, the impassable. And that would make then these chasms that the induction would fail, because not first false is the usual idea that induction carries as long as it's maintained. But then not ultimately untrue is somehow it crosses this bridge, Zeno's bridge. And this gets involved in things like the Turing machine, which is a model of computation from Alan Turing, a computer scientist of the 20th century. That basically the idea is that there's a tape, and so then there's a read and write head on the tape, as of like a tape drive or a cassette tape, but usually a magnetic tape that has values that can be read from the tape, or just a paper tape with numbers or marks on it, and the ability to read and write on that tape. And then the algorithm is what so follows is basically the instruction pointer in usual model computation. So one of the ideas of that is that it's finite, and so when talking about the potential and actual, the infinite, then it's potential. It's unbounded yet finite. And so these Turing machines are given as a model of computation. And there are others like stack machines or various sorts of automata or in any way to like formalize to make regular patterns, drawing with a stick and a beach in the sand, or counting pebbles and making stacks and these sorts of accounts. Then that the Zeno machine is the idea of what are super tasks. So a super task is what happens all the way to infinity. So it usually associated with Zeno's arguments of the half and half and half again of the archer, or as with regards to the passage of an object when its passage is partitionable into two equal parts, and then that occurs infinitely many times, and whether the limit then is the sum attains to the limit that's bounded and finite again is the sum. And so the Zeno tasks, super tasks of a Zeno machine have that this is the idea then that there are at least three accounts of whether at the end whether that completes, whether that goes beyond, or whether it's just right in the middle. And so kind of like Goldilocks and the Three Bears or something like that, but too hot, too cold, or just right. This is along the lines of the idea that there's laws of large numbers, and which basically have it that there's always a large enough number to divide out something else and result zero. And then whether or not it makes it so that then there's one of those that's large enough that divides it out by infinity and equals 1 is the usual idea of there being a point at infinity. So there are at least three laws of large numbers, and getting into the accounts of the mathematics has this as features and facts of mathematics. These are just part of the nature of the objects of mathematics, infinity and continuity. So the giant monsters of mathematical independence are from a time when Paul Erdos, this mathematician of the 20th century, he was studying results in number theory and making accounts of asymptotics and using limit theorems and sandwich theorems and the like to find where these bounds would be. And he comes up with contradictory results. Otherwise perfectly well-founded, each a piece, well-defined and well-posed in the sense of Hadamard, one may aver. But then they contradict each other, and so he calls these the monsters because they're mathematically independent of what these are. So the great atlas of mathematical independence is instead it's the idea of the figure of Atlas holding up these three worlds of models of continuous domains, laws of large numbers, probabilistic limit theorems themselves, the inductive limit, then an infinite limit that's somehow complete, and then a continuum limit that furthermore is giving measure and completeness to. Otherwise, the account of the inductive limits, that these deductive accounts make for a space for something to exist, and then the completion can be said to be so, and in fact it needs to be so to be this way, because otherwise you can take any account of a limit and just break it in half, and then if it's close enough but doesn't quite meet, it just doesn't quite meet. So the inductive impasses, after accounts of induction and the strength of induction, then for the riddle of induction and the fallacies of induction, these giant monsters of mathematical independence, has that this great atlas of mathematical independence is the idea then that in a more replete setting, that these accounts of completeness have this repleteness, so that it's an evolving sort of definition. In the Hilbert's Infinite Living Working Museum of Mathematics, this is all the study of it, all the books on all the shelves and all the libraries of the world, and all the mathematicians, their work. Hilbert's Infinite Living Working Museum of Mathematics, to help make an account of this great atlas of mathematical independence, because otherwise we're just Pythagoreans kind of adrift at sea. And then the great account of that is that the Pythagoreans have everything rational, and then the Cantorians, the modern mathematics, has most everything transcendental. And so there's a contradiction between those two. So trying to figure out how there's the road in the middle, these analytical bridges, that for analytical bridges and continuous domains, then that's mathematical foundations, this account of a great atlas of mathematical independence, which otherwise these giant monsters of mathematical independence have, that many conjectures, like some of Hilbert's problems, are never resolvable. And when they are found to have examples that are consistent, that they're so, that's also that their counterexamples is consistent they're not. Those disagree, so then to have them resolved, in resolving the paradox instead of ignoring the paradox, that's what conscientious mathematicians and logicians in this super classical setting have as course to do, reading in Foundations. Cambridge Tracts in Mathematics, number 162. Levy Processes in Lie Groups by Ming Liao, Cambridge University Press. So processes are the idea of like a limits. So Markov processes, the Paley-Wiener, after Norbert Wiener, but for Markov, and the ergodic. So the ergodic is the idea, kind of like the asymptotic. And so ergodicity is a property of something about whether it's random, and then with regards to accounts of random motion, like Brownian motion and random walks, and these other sorts of accounts of what would result given a value at time 0 and a value at time 1, and then a value at time infinity, what would be the behavior of this process over time. So processes are usually the accounts of a process over time. And then the accounts of here Levy processes, vis-a-vis Markov processes, and the Paley-Wiener processes are accounts of Markov processes. Then this is all an account of ergodicity. So the ergodic and ergodicity is closely related to the stochastic and the random, but as well with the accounts of the behavior at infinity of accounts of processes. So this book, Levy Processes in Lie Groups, have that Lie groups are particular kinds of symmetry groups, and then they also make accounts for that they kind of cut corners is the idea, and so at the same time that makes them as a reductionism to bring some things into being sensible, fungible, and tractable. That sensibility, fungibility, and tractability make what a mathematical approach is to working with all the rest of the mathematical approach, and then having it so to be formalized, so to be sensible versus like in the intuitionistic setting, it's defined, and then in the fungible is that it's relatable in the terms almost universally algebraically with regards to arithmetizations, meaning it's just like numbers. You can treat the numbers by their operations as these objects, their operations, in whatever sort of account. Geometrizations, like arithmetic, but for geometry, you can treat these objects in the of this theory as like geometries. Anything you can apply to geometry would be as of this account. Then algebraizations. So just like that, their usual accounts of algebras have that there are many different structures that each of their own kinds of algebras. The arithmetic is like a monolith, then with these different accounts of independence and infinity. And geometry is like a monolith, and then there's with these different sorts of accounts about continuity. Algebras are very ranging from the very small and finite, just 0 and 1, alternating like a toggle, to an arithmetization, to a geometrization. And what algebra has then for algebraic manipulation of formulas, terms, expressions about constants of variables with independent variables, and expression, the algebraizations. So groups are just one of the most fundamental sort of algebra. It's got an identity element, it's got inverses, it's closed under the operation that it has an operation. So usually this is something like addition or multiplication. These sorts of groups is in their regular arithmetizations. And then the symmetry groups are similar. It's like, well, is it flipped 90 degrees through a quarter of full rotation to going around, and then like the 0 rotation is the identity, and these sorts of accounts. And so there's the rings and fields and groups. And so a most usual sort of account is a ring, because it's closed and then it goes around. And then groups basically just go out, usually is the idea. And then fields have two particular operations defined that are just like arithmetics for addition and multiplication. So here the usual idea of the true arithmetization of the numbers is two operations, increment and partition, not addition and multiplication, and then their inverses, subtraction and division. It says increment in partition, either adding one or dividing by two, and then those in the middle result the same sort of account. That it's two groups, not one field, is a kind of setting that makes the complete ordered field is in the middle of that. But making it for increment and partition instead of the usual account of after the number line is given, after the Cartesian coordinate system is given, after all these accounts of the usual setting for the diagrams of all these other things, then that this deconstructive account of arithmetic is seen to be kind of a true account, and then for the algebras and so on, the Lie groups and these about the analysis of ergodicity, so that analysis is basically what happens in infinite processes and infinite completions. Then that the algebras are in the finite and the discrete. That these are the sorts of accounts where they kind of come together. Here's a brief description. The theory of Levi processes in Lie groups is not merely an extension of the theory of Levi processes in Euclidean spaces. Well, that's because whether Euclidean spaces or Lie groups are considered primary has that they're usually considered attached, but they're not. And so Lie groups kind of follow just a bit outside the usual account of the completions. Because of the unique structures possessed by non-commutative Lie groups, these processes exhibit certain interesting limiting properties that are not present for their counterparts in Euclidean spaces. These properties reveal a deep connection between the behavior of the stochastic processes and the underlying algebraic and geometric structures of the Lie groups themselves. The purpose of this work is to provide an introduction to Levi processes in general Lie groups, Lie, sophist Lie, but it's pronounced Lie. The limiting properties of Levi processes in semi-simple Lie groups of non-compact type, and the dynamical behavior of such processes as stochastic flows on certain homogeneous spaces. The reader is assumed to be familiar with Lie groups and stochastic analysis, but no prior knowledge of semi-simple Lie groups is required. So these properties of the groups, kind of like a Jordan curve is a simple closed connected curve, for example, any kind of shape on a page that has no crossing lines, simple closed connected curve. And so then saying that the semi-simple Lie groups is sometimes this accounts of restriction and comprehension, because what's one thing to say is like, well, it has a structure and it has more structure and it has more structure on that, and it's all one giant structure. It's another to say, well, it has all this structure and then it falls in, and we're only looking at it as singularity, a branch in a multiplicity theory. So that said, then speaking to the Lie groups are already kind of their own detached setting because of a restriction of comprehension, and that's kind of the usual thing. It enables one to make, after sensibility of that, a fungibility of that. It gives a method, an approach, a technique. And then for the tractability to then apply that thoroughly in the analysis of these things. So the arithmetic is kind of divided into analysis and algebra separately. And then the account of the axiomatics has this. So the axiomatic setting is the idea is that there's only these elements of the axiom system, and that's the only thing that exists in the theory at all. And so approaching how to like compose them together is expansion of comprehension. Then the idea of that there's a reductionism or a truncation, a cancellation, a correction, a truncation, approximation, a reductionism has this sort of account of comprehension then as a restriction of comprehension. So the axioms have two roles, kind of like rules and exceptions and rules. On one hand, they expand comprehension, but originally the whole axiom system is like it's limited to that. And so an account of axioms as restricting comprehension has that it's then furthermore that some of the axioms actually after the the free, unfettered expansion and comprehension is restriction and comprehension again, a conscious sort of claiming that. Then later in axiomatics, that's said are to be a fait accompli, but the problem is, and then it's always held so that expansion comprehension, restriction comprehension, like in set theories like ZFC, where there's an ordinary empty set and ordinary infinity. It's one thing to say it's like, well, there exists an empty set, and then another says there exists an infinity, and then expansion and comprehension follows, saying that they're ordinary when, for example, it's like there's not a unique empty set. Each type is its own empty set, or there's not there's an extraordinary infinity. There's fragments, extensions, these multiple models of larger and largest numbers, and empty, emptier, and emptiest empty sets in a sense. Has it that these accounts of the abstractions and the definitions also have these two accounts of whether it's growing or shrinking. So these are then descriptions that a semi-simple Lie group is like a little bit less than a Lie group. And so a theory of semi-simple Lie groups then appended with this other sort of thing is different than a group, and then a Lie group, and then a simple Lie group, and then a semi-simple Lie group. It's about why these sorts of accounts make that in theories of type and about the usual hierarchical association of a top-down type or bottom-up type, that the inversions of these things then have that the branches, when it's restriction and comprehension, narrow, but when it's expansion or comprehension, widen. So narrowing types and widening types is another sort of account in this expansion and comprehension, restriction and comprehension, that according to the structural results, all the relations that so follow, everything that's so fact about these things and all the universal mathematical objects, then has that these are otherwise a bit different than the accounts of rules without exceptions and exceptions without rules, there's a more thorough account, speaking to the dangers of just adhering to the principle of non-contradiction and sufficient reason instead of principle of inverse and thorough reason, that being more general, if less than fungible, in its own account more sensible, then the account of the fungibility, being able to affect something, to manipulate something, and then the tractability to carry it out in an automatic infinite sense for forever, sensibility, fungibility, and tractability. These are the sorts of accounts. Structure coefficients. Elworthy, Ikeda, and Watanabe ensue. In this section, we consider several cases when Riemannian-Brownian motions appear in Lie groups in the associated homogeneous spaces. Let G be a Lie group, and let the tuple pair ... be an inner product on the Lie algebra G of G. The latter induces a left invariant Riemannian metric, the product and for the elements on G, under which the left translations L sub G for G and G are isometries. Note that a Riemannian-Brownian motion G sub T in G with respect to this metric is the left invariant diffusion process. That is a continuous left Levy process in G. We will express the Laplace-Beltrami operator delta in terms of left invariant vector fields on G, and from this expression we will obtain a stochastic differential equation satisfied by G sub T. So bringing together these accounts of algebra and analysis, that's giving, much like the propagation of a wave equation, having that it also has a wave model, and then it's like a spiral model. Here, putting together these accounts of the invariance, and then the quasi-invariance for like a wave spiral and spiral wave model, help effect to reflect that all these different models relate to each other by their structure and form. So that's another way to think about what this says. An example, much development relating it to the exponential, relating to the differential properties of the exponential. The Riemannian metric tensor, the left invariant metric on G, induced by the inner product on G can be written as this account of a difference formula after the Kronecker delta of this and that. It's a difference formula, or it would be then for these sums, because on the one side is a Kronecker delta, which is just kind of like identity in the matrix, and the other side has got sums of coefficients by powers to variables, to terms, and then with an approximation let in, or on the order of the absolute value of the x squared, or the magnitude, or for the trace and the determinant, and these sorts of accounts about when these then make for accounts of reductionism, and adding in the terms for the approximation, what's the truncation, the cancellation, the correction, what results then, these are equal, yet with the other terms on the side, which then are given accounts of in courses when they go to zero, and are negligible vis-a-vis when they're non-negligible. So there's a lot going on. There's all the free play of the objects of analysis in these algebras. And then these are expressions with their implicits about the formulation of the terms, meaning interacting terms that, for example, compound or square each other or anything like that. That gets into the idea of that anything divided by a large number goes to zero, except one large number which stays the same. So that's the accounts of the negligible and non-negligible. Then when these terms explode, they're sometimes said to do or dominate the expression, and when they don't. And these are the kinds of ideas. 3 decompositions. So much about the left Levy process. So in formal automata, there's like a acceptors and rejectors, and then left and right linear, these accounts of formal automata. And so then that simplifies a lot of things when it's just one way. And then figuring out what happens in under alternatives and options then is a greater account, and also involved in natural language parsing and these sorts of things. So this is a very deep book. The limiting properties of Levy processes may also be studied from a dynamic point of view. If the Lie group G acts on manifold M, then a right Levy process G sub T and G may be regarded as a random dynamical system, or as a stochastic flow on M. So the difference between the random dynamical and the stochastic is not much different. Except that one is the count of varying the parameters of the dynamics, and the other is the count of just adding up the differences. So this gets involved, like in the various settings of change. What are the increment in partition? That's so fundamental. Perhaps one of the deepest discoveries in probability theory in connection with Lie groups is the limiting properties of Brownian motions and random walks in semi-simple Lie groups of non-compact type, both of which are examples of Levy processes. The celebrated Levy-Kinchin formula provides a useful Fourier transform characterization of infinite divisible laws, or infinite divisibility laws, or distributions of Levy processes on Euclidean spaces. For Levy processes and Lie groups, there's also a natural connection with Fourier analysis. So Fourier analysis is a very well explored idea of being able to build a function from all these other functions. It's an infinitary result. It's a completion result. The Fourier-style analysis of the Fourier series first, and then the Fourier transform is after that. With regards to a Fourier process, that these are the sorts of things. Fourier methods. Here that's just called Fourier-style. Fourier analysis, Fourier methods. And then introducing, for example, Haar measures, and so the convolutive setting when these Lie groups with their non-commutativity, not being abelian, not being reversible, have it then these the accounts of the Haar measures is like, well, this is, if you build this back up, then this would give an account of what it should be when it fills back in. Very recently, the author Liao studied the Fourier expansions of the distribution densities of Levy processes in compact Lie groups based on the Peter-Weil theorem and used it to obtain the exponential convergence of the distributions to Haar measures. So, kind of figuring out when a balloon fills a box, how it reaches the corners. Figuring whether it's being drawn out of the box or whether it's filled from the inside. So inner and outer products. Like the simple additive structure on a Euclidean space, the more complicated algebraic structure on a Lie group provides a convenient setting under which various stochastic processes with interesting properties may be defined and studied. An important class of such processes are Levy processes that possess translation invariant distributions. So these are a translation invariant means it doesn't matter how you move it around, it stays the same. So shape and scale and the invariant and the affine and the conformal, what geometry says is invariant. Since the Lie group is in general non-commutative, there are two different types of Levy processes, left and right Levy processes, defined respectively by the left and right translations. Because the two are in natural duality for most purposes, it suffices to study only one of them to derive the results for the other process by a simple transformation. Here, getting into the adiabatic, which basically is like one of these, left or right. And the non-adiabatic has that, does get more involved. And here, that's with regards to the Duhamel principle and the integro differ and different integro. That being considered general. Note that a Levy process may also be characterized as a process that possesses independent and stationary increments. So that it works out to be increments, and then it's incremental. A path, a line. The Pocket Stoic by John Sellars. He says, no one in their right mind goes out looking for adversity. But at the same time, it's like that's how things are. These were the cynics, the most famous of whom was Diogenes the Sinope, who is said to have lived for a while, at least in a barrel, like a stray dog. Diogenes is a traditional character. For Socrates and later the Stoics, this concern with taking care of one's soul has that the Stoics are considered minor philosophers, but they speak to people. Immanuel Kant, prolegomena to any future metaphysics. So Kant here has in this a revision of the Caius translation with an introduction by Louis White Beck. This prolegomena to any future metaphysics, saying these are his requirements and desiderata of what would be an account of the theory overall. So here the theory overall is called thea-theory or the a-theory, two different terms, one being just a word, thea-theory, and the other being a phrase, the a for axiomless theory. That Kant here, when he's as part of the analytical tradition, is still associated with the idealistic tradition. And so then with regards to whether that's called continental philosophers, vis-a-vis analytic philosophers, here is that it's always both, because having ideas or axioms at all is its own kind of ideal in an analytic setting of accounts of definition. So then to get out from what Kant says is first consider just a pretty much a rational Epicurean sort who has that there's only available to our senses what is interrelatable, like this spoken word account, if you can hear it, or the words on a page, if you can see them. These accounts of what you can see or according to the senses. And then what's the noumenological, that the nous or the noumenon is the mind, and then with regards to what exists in the mind. And the idea that these Platonic ideals of mathematical Platonism exist not just in our mind, but they exist in reality. That the only reason our mind can comprehend a straight line or a perfect circle is the true somehow. So truth is the idea. So Kant has then his requirements, criteria, judgment. A lot like Descartes, who's like, you can't fool me. I use science, this is I will think about what I hear and not just accept it and think it. That when you have thoughts, you are thinking about them, not just thinking them and being dragged through them in a sense. That an inductive course is doomed to a chasm of after an inductive impasse is not guaranteed, vis-a-vis that the accounts of the deductive analytical bridges with their completion results are guaranteed, and these sorts of things. So then, besides this critique of pure reason, here Kant's just making a manifesto. What would say that this would be a requirement for any sort of future metaphysics, which here is this thea-theory. It's not a meta-theory. It's not a metaphysics. It's a theory itself. Whereas the metaphysis or metaphysics is, since Aristotle just kind of his notes about it, but it's like this is our ground laws or reasoning apparatus about it. And so the metaphysics then is or metaphysis and vis-a-vis the metaphysica. Here is that that's just the theory, the full account of the theory. So to have a monoheno theory, one theory that also interprets and expresses all the other theories in one theory, and as well to have that sensible, fungible, and tractable. Here's made as after complementary dual, is that there is one. And then it starts with language of truth, communius language, with all the metonymy, Kabbalah, the gematria, all the names and numbers of things. And then in our Coleridge language, we talk about it, or can think about it in so few words. Then that Kant here is going to say something about his theory, his meta-theory, his metaphysics, and then what he would intend to say to that. The Library of Liberal Arts, Oscar Piest, founder, P-I-E-S-T. The Bobbs Merrill Company, Incorporated, Indianapolis. Copyright 1950. Originally published in 1783. 13th printing, 1975. So in this prolegomena to any future metaphysics, there's an introduction, then the preamble on the peculiarities of all metaphysical knowledge. The first part of the main transcendental problem: how is pure mathematics possible? It's the usual kind of ideas is not possible, and so expansion and comprehension is that it's a sole sort of truth. It's a sole sort of foundations. Second part of the main transcendental problem: how is pure science of nature possible? Science is our account of the study of it, and so the theory of it, and then to get to the axiomless physics it would have to start with axiomless mathematics and having a great atlas, as it were, of mathematics. Third part of the main transcendental problem: how is metaphysics in general possible? Conclusion on the determination of the bounds of pure reason. Solution of the general question of the prolegomena: how is metaphysics possible as science? Or vice versa, how is science possible as metaphysics? Introduction. First is the note on the text. It says the prolegomena has appeared 4 times in English, translated by Richardson, London 1836, Mahaffy, London 1872, and Bax, London 1883, and edited in English by Karras, Chicago 1902. Two rather significant changes have been made in the organization of the text of sections 2 and 4. The last 2 sentences in the paragraph on page 16, which begins with the sentence, just as little as any principle of geometry analytical, have been moved to this position from the end of the paragraph immediately following. The 5 paragraphs commencing with the words, the essential and distinguishing feature of pure mathematical knowledge, page 17, have been moved to this position from section 4, when in the original context they were included as the second and 6 paragraphs. Kant's prolegomena, its full title in the 18th century manner, is Prolegomena to any future metaphysics which will be able to come forth as science, is a classic of metaphysics and the theory of knowledge. So here the idea is the logical positivism, all it has is science to begin. So all the axiomatics, the usual account is science. And so then people say, well, then mathematics must be a science and logic must be a science. Well, that's not necessarily so, because those can exist for their own account, just because the reason and rationality can't not arrive at that there's a straight line and a perfect circle. Mathematical truisms, well, at the same time, can't not arrive at that there's no way to have one in real life, only in our mind, our minds together, or apart for that matter, or even if we weren't around. So this is the whole account of the analytical tradition is science, and this is only justification. But then the knowledge, you divide the accounts of knowing something, intelligence and wisdom, and knowledge and science. So intelligence is just kind of the capacity to think over things over, and wisdom is haven't done that in experience. And then science and knowledge basically has knowledge as science, and a science of knowledge. And these are the sorts of accounts. Talking about Hume. Hume suffered the usual misfortune of metaphysicians, of not being understood. This is still in the introduction. But Hume, I read about Hume's connections over here. Hume brings back like the modal temporal relevance logic at a time when it was getting quite Boolean and just way disconnected from reality. This was Hume's problem, not Hume's problem of induction. It was solely a question concerning the origin, not concerning the indispensable need of using the concept. It's not so much the indispensability of a concept as the fact that it's always there, and it always offers itself as kind of like the perfect circle or the straight line, these being considered mathematical ideals. Then for continuity and infinity, that they do too. So that continuity and infinity are real. Talking about the proviso or the gift as from we can't consider ourselves anything more than kind of profane in the sense of the micro scale and the macro scale, or the super and the omni, that it's considered a gift or a proviso, regardless of its origin in a sense. And the difference between like common sense, as it's called, and science, when it's kind of when the unintuitive and this kind of thing has here, there's no distinction thereof. That all of that is both common sense and science. He's talking about first part of the main transcendental problem. How is pure mathematics possible? Kant, Immanuel Kant. Here's a great and established branch of knowledge, encompassing even now a wonderfully large domain and promising an unlimited extension in the future, yet carrying with it thoroughly epideptic certainty. That is absolute necessity, and therefore resting upon no empirical grounds. Consequently, it is a pure product of reason, and moreover, it is thoroughly synthetical. Hence the question arises, how then is it possible for human reason to produce such knowledge entirely a priori? Maybe it's the other way around. Does not this faculty, which produces mathematics, as it neither is nor can be based upon experience, presuppose some ground of knowledge, the a priori, which lies deeply hidden, but which might reveal itself by these its effects if their first beginnings were but diligently ferreted out? That's the idea. Yeah. But we find that all mathematical cognition has this peculiarity. It must first exhibit its concept in intuition, and indeed a priori, therefore in an intuition which is not empirical but pure. Without this, mathematics cannot take a single step, hence its judgments are always intuitive, whereas philosophy must be satisfied with discursive judgments from mere concepts. Though it may illustrate its doctrines through an intuition, can never derive them from it. There's an account after the void and universal, the point in space given axiomless geometry, and the increment and partition given axiomless arithmetic. So then there's also continuity and infinity, because the reasoning, the account of the inversion and thinking things over, the knockabout of the Entbergung of these things, still makes for that. Then there's the independence is discovered, mathematical independence, and then the monsters and the atlas of the mathematical independence has that. It's the usual classical account is it's discovered, not invented, and then the later account, it's analytical, is like we can invent something and then agree to that its parts move the same way. It's also so, and then with regards to how that can be kept as an object of reason, has a, these would live in Kant's noumenon, in his mind, and they do so because they exist in his worldview and model of the world of the Platonic existence of these mathematical ideals. So one imagines Cicero might have read this about his in the greater account of the 20th century is like we're done with the analytical tradition, or we're entirely inside it, but geometry is still perfect. And so then trying to figure that out in the Meditations of Edmund Husserl is it's kind of the same sort of discourse. But Kant here seems happy and pleased enough to presume a priori that the mathematical objects exist. Talk about appearances. Locke, idealism. So he says something about idealism, or in the translation. Quite a thorough account of, and it's kind of like Descartes, being honest with himself about his limitations. How is nature in the material sense, that is, as to intuition, or considered as a totality of appearances, possible? How are space-time and that which fills both, the object of sensation, possible generally? And then the answer is, by means of the constitution of our sensibility, according to which it is in its own way affected by objects which are in themselves unknown to it and totally distinct from those appearances. So the accounts of all relation in a universal sort of sense. This answer is given in the Critique itself in the Transcendental Aesthetic, and in these prolegomena by the solution of the first general problems. Secondly, how is nature possible in the formal sense as the totality of the rules in which all appearances must come in order to be thought of as connected in experience? The answer must be this. It is only possible by means of the constitution of our understanding, according to which all the above representations of the sensibility are necessarily referred to a consciousness, by which peculiar way in which we think, namely by rules, and hence experience also are possible, but must be clearly distinguished from an insight into the objects in themselves. This answer is given in the Critique itself, in the Transcendental Logic, and in these prolegomena, of course, the solution of the second main problem. So these are basically the primary tenets of the analytical tradition. They're a priori judgments given to it. So these are sorts of its axioms. And then the scientific approach is a stronger account that so follows. And then the even stronger account of logicist positivism is not just that it's a science, because Kant here says it's just kind of the rules, and then also that it's the science, and then it lives in a mathematical universe. So these being judgments. So talk about Aristotle's 10 pure elementary concepts, and then in the categories, the predicaments. Here we read the philosophical predicament. That was considered very good, of the Winston H.F. Barnes. To the dialectic of pure reason, and so on. So that's just an account of Immanuel Kant's and the prolegomena to any future metaphysics. Here there's kind of the axiomist theory or a theory does not have a metaphysics. It's its own metaphysics. A thing in itself, as Kant might say. Integral equations and elasticity by V.Z. Parton and P.I. Perlin. Mere Publishers, Moscow. I'm going to put this in my stack of differential equations, integral equations. So I just have like 30 or 40 books on integral and differential equations. And I'm trying to get it about half and half, integral equations and differential equations. So this says, the classical investigations of Fredholm, Hilbert, Poincaré, Muskelishvili, Tricomi, Giroud, Miklin on the theory of integral equations, one-dimensional, multidimensional, regular, and singular, determine the success of their application to the solution of boundary value problems in mathematical physics, in particular in elasticity. So elasticity is great because it's got creep and relaxation, and also the restitution. So it's got oscillation, restitution, and attenuation and dissipation. So elasticity is almost always with continuity equations instead of conservation laws, because it's not adiabatic. It's kind of the usual idea. And so here for these, it's the dynamical systems that also tend to reform themselves. As is known, only in exceptional cases are the integral equations amenable to analytical solution, and their use therefore became possible only with the advent of high-speed computer facilities. Taking into account the increasing interest of specialists engaged in elasticity theory and its various applications, here about integral equations, it's just kind of like the whole study just kind of started ignoring them and focusing only on differential equations and using solvers for those. And so that's a bit of a strong opinion. The authors have made an attempt to present the most important achievements in a form intelligible to scientists, engineers, postgraduates, and undergraduates. On integral equations for fundamental three-dimensional problems of the theory of elasticity. Completely continuous operator, regions in the plane for which the minimum value is 0. Let us prove that in any other regions, the index remains constant. Consider now the question of equivalent regularization by a procedure suitable also for the case of closed surfaces. So procedures resulted in these processes. Expressions in the Laplacian. So Laplace and Poisson, Gauss and Ostrogradsky. Method of linear relationship. Let an infinite elastic plane be weakened by a doubly periodic system of cuts parallel to the real axis. See VZ Parton and B.A. Kudryavtsev and VZ Parton. In the class of doubly periodic problems of the theory of elasticity, most studies are concerned with the equilibrium plates and shells with circular or elliptical holes, perforated plates and shells. However, similar problems for straight or curvilinear cuts are also of interest in applications. So here there's the regulus to consider, which is like a plane is just all these straight lines in parallel. And so is any way you bend it and twist it. So is a cone. So is there many things have just straight lines all the way through them. And then the identity dimension, which is the singularity, and it's an envelope of linear fractional equation, Clairaut's equation, and D'Alembert's equation, among many integral equations. Much like 0 is a trivial solution, the identity dimension is the trivial envelope of these integral equations. And so that offers a setting, so the complex numbers and complex analysis, this identity dimension analysis, some kind of thing. Here's Edmund Husserl, Cartesian Meditations, an introduction to phenomenology. This is translated by Dorian Cairns. So this is the Cartesian Meditations, vis-a-vis like Derrida's reading of the Meditations. So this is kind of mentioned a bit, so I'll just pass it along. G.W. Leibniz, Discourse on Metaphysics and the Monadology. So this is a bit perhaps broader than the monadology itself. This is a discourse on it. Introduction by Paul Genet, Discourse on Metaphysics, the Monadology. So first we'll look to see here how he's the same or different as Kant. To avoid the difficulties inherent in this theory, the schoolmen were led to adopt infinite divisions among the substantial forms. This way the Jesuits of Coimbra admitted 3 kinds of these forms. First, the being which does not receive its existence from a superior being and is not received into an inferior object, this being is God. Second, the forces which receive their being from elsewhere without being themselves received in matter, these are the forms which are entirely free from any corporeal concretion. Third, the forms dependent in every respect which obtain their being from a superior cause and are received into a subject, these are the accidents and the substantial forms which determine matter. So accidents are not unintended mistakes. Accidents are just consequences of order and causality. So they're just what follow. These are the accidents. Other schoolmen, so these are about the Peripatetics and the Schoolmen. When Descartes, in the first half of the 17th century, this is from Genet's introduction, so there were only 2 types of things or substances in nature, namely extended bodies and thinking substances, or bodies and spirits, that embodies everything as reducible extension. So this is kind of just like the distinction between the phenomenological and the noumenological. And then the super and omni is given its own place. This is also given for Aristotle. It says three different things that don't really agree. Circular movement is eternal. It just keeps on spinning. It keeps on going round and round. Time keeps on slipping. There is no unmoved mover. Something had to move it. And this is usual account of the conservation of forces and all this kind of stuff that ends up being sensible, fungible, and tractable since Lagrange in his, the mechanics. And then the motion of the stars is voluntary, and that's just like the outside account of the ergodic, as it were. Metaphysics. Leibniz. 1. Concerning the divine perfection, that God does everything in the most desirable way. This is basically the idea that if there's a truth and mathematical objects are pure and true, then it's God's own theory and it's true. And then our ideas of it is still, it's like, well, it's just a gift and it's just a given, and so it's just got to be true and perfect and pure in every way. So that's just the account. Then it has to be everything that it can be somehow altogether infinitarily, and is perfect and true and complete and replete in every way. So that's mathematics. Or math, it's math itself. The object's mathematics. There are many different kinds of perfection. So we're talking about the supreme and the omni. And giving that this is the divine perfection, or just perfection here, and that it exists. This is just a great defense of the idealistic tradition that the strong mathematical Platonism has perfect circles and straight lines. And how it gets there and arrives to be that way under all considerations is also so, and something we attain to this in this thea-theory that is like so. So that's given as just a universe of truth. So the universe of mathematical objects falls from a universe of truth, is the idea. And then that's related to various accounts that would be relatable to Leibniz in his language, helping to express that the terms like Heidegger's use of Dasein instead of deity, or perfection, or the proviso instead of like the gift, or that. Has that then the voluntary submission and attachment to that is a conscientious act. It's very defensible. That without necessarily attaching the baggage or violating free will or freedom of religion. That's the idea. The extraordinary intervention of God is not excluded in that which our particular essences express, because their expression includes everything. Such intervention, however, goes beyond the power of our natural being or of our distinct expression, because these are finite and follow certain subordinate regulations. So that's just the usual account of that, the universalist account. An example of a subordinate regulation in the law of nature, which demonstrates that God always preserves the same amount of force but not the same quantity of motion, against the Cartesians and many others. So this is account after vis-viva and vis-motrix and the vis-insita, the forces of the rectilinear, the motrix, and the viva, the active or living force, and the insita, that which is kind of contained within the object. Here there's a kind of space contraction rotational, and space contraction linear is different. So with Descartes with subtle matter, here is that on the one hand you think that Leibniz is trying to break open Newton, who's like vis-motrix, and Leibniz is like, well, vis-viva, and then Descartes was like vis-insita. That these are different counts of motion and force and stuff like that are going on. Then they would cast and say, well, like this must be an eternal truth. And so these are aspects of the giant monsters of mathematical independence rearing each other's ugly heads to each other. So then the idea of like the Hydra and cutting them off is actually, it's just like, think of it from the Hydra's point of view, is like how to become an atlas instead of a giant monster. Monsieur Descartes and many other clever mathematicians have thought that the quantity of motion, that is to say the velocity multiplied by the mass of the moving body, or inertia, or the energy of the thing, is exactly equivalent to the the moving force, or to speak in mathematical terms, that the force varies as the velocity multiplied by the mass. Now, it is reasonable that the same force is always preserved in the universe. So also looking to the phenomena, it will be rarely seen that mechanical perpetual motion is impossible, because the force in such a machine, being always diminished a little by friction, so ultimately destined to be entirely spent, would necessarily have to recoup its losses. And so this is conservation, or continuity law. And consequently, it would keep on increasing of itself without any new impulsion from without, perpetual motion. And we see furthermore that the force of the body is diminished only in proportion as it gives up force, either to a contiguous body or to its own parts, as far as they have separate movement. So this is perfection, principle of perfection, gaplessness, Leibniz. So this is great because this discourse on metaphysics is about physics and mechanics. And these are requirements in desiderata that go into all the different things. So here from the moment in motion bit here, arriving at world's turn after geometry is motion, and making for accounts of why there's room in the theory for these, and close to like the first and second order terms after the truncations and reductions that arrive, the definitions have just let out that this goes on the physics shelf. Then the Monadology is an account of like a universal, holistic kind of thing. Well, that's the hour or so. I haven't got very deep yet in this box of books. But this is philosophy of physics, it's philosophy of metaphysics, and so it's metaphysics. Transference methods and analysis. The Conference Board of the Mathematical Sciences, Regional Conference Series Mathematics, number 31, American Mathematical Society. Supported by the National Science Foundation, published by the American Mathematical Society, National Science Foundation. Ronald R. Koifman and Guido Weiss. Providence, Rhode Island. A conference series. Transference, some classical examples of transference. Calderon, Kotler, Hertz, and Zygmunt, I imagine. Interplay between properties of convolutional operators on classical groups G, such as the integers, the reals with the torus, and operators associated with more general measure spaces. So, HAR, convolutional, a lot of these different analytical counts are all talking to each other without so much saying so. Algebraic groups and modular Lie algebras, again, James E. Humphreys, Memoirs of the AMS, number 71, published by the AMS, 1967. Again, many disparate accounts, all alike. The Story of Philosophy by Will Durant. I have another edition of this. And so this is this is a little bit shallow. Bacon's frank acceptance of the Epicurean ethic. Yeah, he is about William James and Dewey, John Dewey. So. Yeah, I don't have much for that account. So anyways, general readers, a bit of metaphysics today. Not metaphysics. Warm regards.